Okay, it looks like we've kind of plateaued and we have an excellent turnout today. So thank you, everybody. And I'm going to kick it off from here. Um, Welcome to the fourth webinar in Groome's series of monthly value-add presentations titled SCR, Cradle to Grave, Lifecycle Management and Replacement. The turnout, like I said, has been incredible so far, and this presentation has definitely been the most anticipated yet. As you can see, we've covered a diverse mix of topics so far. This is the fourth in our series. We've covered everything from properly disinfecting your facility during a turnaround or outage, and that is as topical today as it was in March when we presented it. So what we found is that no matter how different these topics are, we've seen great success stories come from them all, from each industry, whether it be a refinery, HRSG, or even waste to energy facilities. It's our full expectation to offer you insight on what to consider at your plant regarding SCR services on the presentation today. A little bit of housekeeping before we get the show on the road. On the agenda side, we're going to discuss SCR basics at 30,000 feet. Now, we only have 40 minutes to discuss a lot of material, so please feel free to post questions on the Q&A board. We'll address anything that's not fully addressed in the body of the presentation. We're also going to discuss what to consider when looking at SCR replacement by allowing you to put yourself in the manufacturer's and contractor's shoes. We're going to have Dave and Ryan discuss and introduce perspective from the manufacturer and contractor side. We're also going to discuss what's in it for you. Best way to do that is introducing some case studies and talk about some projects that we've completed to bring things closer to home, and also wrap it up with the return on investment that we were able to realize for our customers on those projects. And finally, as you see, this presentation is being recorded, so a link will be sent to all registrants by tomorrow once we have it cleaned up for you. Quick introduction of the three presenters. I'll start with myself. My name is Steve Houghton. I'm the VP of Sales at Groome. I oversee the 5 divisions on the sales side. Today, we're going to be discussing services on the HRSG, refining, and petrochem divisions primarily. Next, Ryan Esposito is Groome's esteemed engineering manager. He's got 8 years of SCR expertise, 5 years of which have been at Groome, where he's been focusing on design, maintenance, and retrofit of catalyst systems. He's a fantastic resource and a wealth of knowledge. I think you'll find that pretty quickly. Please feel free to call him and pick his brain anytime. And last but not least, David Taylor. He's Umicore's sales manager with 6 years of experience at Umicore. He's got a long history of experience in power generation and refining and petrochem. We welcome his insight and support and thank him for joining us. With that said, Dave, I'm going to pass it to you to introduce everyone to some SCR basics.
Perfect. Hey, thank you so much, Steve. So first, I just wanted to start off with a kind of general overview of what an SCR reactor looks like. For those on the call that work in the refining industry, this might seem familiar. This will be a similar layout to an FCC unit or a fluid catalytic cracker unit. So here, this is kind of the same way a lot of SCRs are laid out, where you have an ammonia injection system, and then further downstream, you have the SCR catalyst after the reagent, which is ammonia, is injected. And then further downstream, you have a duct where N2 and H2O are the end products after the denox reactant. What I wanted to do is go over kind of a really good overview, I think, of what is actually happening in the SCR reactor. Because a lot of folks just see the reactor sitting there and don't know the chemical reaction that's actually happening. So we have a divanadium pentoxide active site, and that is the actual active ingredient in the catalyst. So it is on a titanium dioxide substrate, and then what happens is ammonia is injected into the system, and it attaches to the vanadium active site. And ammonia sits there, and it waits for N2 or NO in this case, for what we're showing, to enter the reactor. There's a chemical reaction with the ammonia and the NO, and then after that reaction takes place, the end result is H2O, N2, which we breathe in the air, and then the active site is available again for the reaction to happen. And this reaction happens millions of times, almost instantaneous. And this reaction just keeps going on and on and on, and as long as the catalyst is active.
Great. It's always good to have an engineer introduce those formulas. I certainly couldn't do that. Thanks, Dave. Next to go on to, I think is a great illustration of life cycle management. It's a view from 30,000 feet. It's a 10-step basic factor dial to consider in managing the life of your catalyst. Just like buying a car, there's a lot of assumed or unassumed in some cases factors to consider. So when you're buying a car, you need to factor in fuel mileage, oil change cost, tire rotation, air filters, washing, waxing, new tires, new brakes. Those might all seem like common sense when you're buying a car, and how long you're going to maintain that car and what it's going to cost. This right here is a cheat sheet on how to manage the life cycle of your SCR catalyst. If you don't pay attention to half of these factors, it's very likely that your option is going to be very expensive, and that outcome is going to come faster than it should. Just like if you don't change the oil on your car for 50,000 miles. It's very important to be proactive with life cycle maintenance, a lot of times with a qualified partner, which will allow you to realize three things: lower overhead, longer CapEx asset life, and less risk of unplanned or emergency work, which no one wants going into this busy fall year-end outage turnaround period. If you look at the dial here, you'll notice that nearly half the steps for catalyst management don't even touch the catalyst itself. On the right-hand side in gray, you'll see ammonia injection cleaning, ammonia vaporizer cleaning, injection grid tuning, modifications and upgrades of the ammonia system. With that said, it's extremely important to have a partner who knows your system, because this is not merely a simple labor support function. Now, to change gears for a second, I get to introduce the cheat sheet, is how I like to put it, of SCR replacement projects. Dave and Ryan are going to talk from behind their desks on exactly what's taken into consideration for a project. These are the guys who play an integral role in designing your system to perform based on how your unit is expected to run. System design is not like building IKEA furniture or like Legos with your kids. Every system is different and unique and needs to be treated that way. So to shift gears again, we're going to start with the manufacturer considerations and hear those considerations from Umicore's perspective with Dave.
Oh, thanks, Steve. Okay, yeah, so I just briefly wanted to cover kind of the reasons for catalyst deactivation. And the one important thing I want to get across is every application has unique ways that the catalyst deactivates. In the refining world, a reformer, most of the deactivation that occurs is coming from the chrome tubes upstream of the catalyst that eventually leaches off and makes its way to the catalyst. In a boiler system, it could be a tube leak where the water chemistry from the tubes actually is a catalyst poison, and that will steal some activity from the catalyst over time. An FCC unit, also a whole bunch of deactivation that could occur from PM over time, how the unit is run, fuels. So we take every type of application, and we have a database of what deactivation we expect, and we use that to build our model on how we design the catalyst. So another thing we have to consider is when we get the flue gas information from either the OEM or the end user, we have to design around certain outlet conditions. NOx outlet is one of them, ammonia slip. If we're using the dual function catalyst, which we'll speak to a little bit later, it's CO and VOC is an important one. Another interesting thing I wanted to point out is we're seeing a lot of air permits lately that actually call out formaldehyde. So that's something that is kind of a more of a recent thing that we've seen in the industry, that formaldehyde specifically is being called out. Sometimes SO2 oxidation is a critical factor, and we do have very low SO2 oxidation, just the inherent way the catalyst works. The ABS dew point could be a factor if you have high SO3 concentration in the flue gas. And in the Herstig world, pressure drop plays a critical role because it steals megawatts from you. And on the same way, pressure drop plays a critical role in the refining world if refractory fiber builds up on the catalyst. So these are all design criteria we have to take into consideration. Another thing I wanted to say is, some units were designed 20 plus years ago, and some of the emission regulations, they are not static. They're changing over time. Regulators change the rules. If a unit is repowered, it might have a whole different set of regulations put on it than it had before. Another thing we're seeing, which was a bit unexpected when it first happened, is the way renewables are changing the way the power, especially the power industry works. There were a lot of gas turbines that were designed to run 24/7, but now, especially in places like North Texas and California, where wind and solar has really changed that dynamic, they can only be running for a couple hours a day. And the emissions, especially the CO outlet, is much different than what is originally designed for. So that's something that everybody has to consider, that conditions aren't static from what they originally designed for. So just keep that in consideration. Temperature plays a role also. If we had to find a sweet spot for the catalyst, it's somewhere in this 662 Fahrenheit range. This is a bit dramatic, this curve. It flattens out a bit above this temperature. But I just wanted to stress that there is a sweet spot for the catalyst. We do have a low temp catalyst, which works really well in conditions 400 degrees Fahrenheit. So if there's something like a package boiler where it only sees really low temperatures, we do have a new catalyst for that. And then when it's really high temp, we actually have to design the system completely differently. We have to put less vanadium, which is a bit counterintuitive, but putting less vanadium on the catalyst actually helps with thermal sintering. But when you design for these high temp units, right above 950 Fahrenheit, in that range, there's a lot more considerations you need to take than a design at 600 or 700 degrees Fahrenheit. So just keep that in your back of your mind. Another thing that comes into play is the pitch of the catalyst. So when I say pitch, it's the actual opening of the cells in the catalyst. A lot of this is driven by the particulate matter in the flue gas, and that information is given to us when we design the unit. So we typically try to use a smaller pitch catalyst on something like a natural gas fueled turbine per se, or an engine. But that's not always the case. In fact, in some of the refinery units that are burning natural gas, we intentionally use a larger pitch to help with some DP issues that could occur with refractory fiber. And more often than not on these units that were designed with 90-degree ductwork upstream, there is refractory fiber issues. So it's not unique to any individual unit. It's kind of seen across the board. So one thing I wanted to touch on just briefly is we do have this catalyst, we call it the dual function catalyst. So it's used in a whole bunch of different applications: gas turbines, engines, cement units, boilers, kind of everywhere that has CO, VOC, and NOx reduction. So what we're able to do is take out the conventional CO catalyst and replace it with this dual function catalyst that does everything all in one element. So it has vanadium and palladium, which is selective for the oxidation of all of the things we're looking out for, especially ammonia. Another thing I wanted to get across is for folks that have units that are looking to replace their catalyst is please don't wait for the last minute. Our lead times are somewhere around 6 months typically. That hasn't changed much with COVID. So if you are thinking of changing out your catalyst, please let us know in advance. We do have the ability at times to work with shorter lead times, but we have to change the schedule around. So please just keep it in the back of your mind. If you are thinking about changing out the catalyst, it's better to look at it sooner than later. Don't wait. Another thing to consider is, so we do a design for the catalyst, and we give guaranteed values. So that's end of life values. So for the refinery folks on the call, we try to design those around your turnarounds and give you a little bit of safety margin as well. So if you have to extend the turnaround, you're still meeting the outlets that we we define. And in the power world, it's a bit different. We're trying to balance out the guaranteed reductions and at the same time maximize the activity of the catalyst so there's not as much pressure drop. Because if there's pressure drop in a power unit, you're losing megawatts. So it's kind of a balancing act on both sides.
Excellent, Dave. Fantastic insight. Thank you very much for that briefing and specifics. So what we're going to do now is discuss contractor considerations by looking at it from the contractor's side of things. I'm going to introduce it and then hand it off to Ryan to discuss some of the specifics. Now, there's 7 main variables that are essential to plan around. Every project is different, could be more, could be less, but you know, in any normal project, any standard project, this is what we definitely need to look at. First off, is the unit equipped with a trolley and a hoist? Or will we be using a crane? If we're using a crane, what kind of crane access do we have? If we're using the trolley and hoist, are they rated for module load? What kind of condition are they in, etc.? Primary factors to consider here are speed and safety, and Ryan's going to dig into that quickly for you. Is the lifting yoke available? You know, looking at the yoke in this picture, it's nice and bright and yellow. Definitely looks like it's in decent shape. I think you've seen in previous pictures that it's got a weight rating painted on it. That's not always the case. You know, we all know that you might have a yoke, you know, at your facility, but you don't know the last time it was used or if it was if it's rated for any kind of weight. So another factor to consider. Third, how is the top door secured? This might seem like a real simple question, but if the print says that it's bolted, we need to you know, double check that. It's not uncommon to find that it's bolted and welded, although the print doesn't say that. What type of catalyst retention is used? I'm going to discuss that in detail. We need to plan in advance if we're going to need new clips and fasteners based on module design and or condition of the existing hardware. Next, how is the frame structurally supported? Is it sound? Is it warped through heat cycling? Again, you know, it's not always plug and play. Next, how is the reactor sealed? If you have the Ferrari of catalyst in your unit, but you're seeing bypass, it's something that we need to consider. One factor that we've been seeing more often over the past couple of years is the frame walking if it's in a horizontal application or vertical stance. Lastly, are engineering drawings available? It's very important to have drawings, but it's more important to have clear drawings that are accurate and up to date. With that said, I'm going to pass it to Ryan to get into a little bit more detail on each variable.
Appreciate that, Steve. So I'm going to start off talking about bypass. Bypass is one of the biggest things to consider when replacing your catalyst, or even if you're just diagnosing a system issue that you may have. Bypass is defined as any exhaust that travels past the catalyst without coming in contact with the catalyst. And it only takes a small amount of bypass and you can quickly find yourself, you know, not being able to meet your system's requirements. So how does this happen? There are 3 primary seals in a SCR reactor. There's inter-module seals, which are between the modules. There are intra-module seals, which are within the modules themselves. And then there are perimeter seals, which go around the perimeter of the catalyst and seal between the catalyst wall and the, you know, the sides of the unit, the top of the unit, the bottom of the unit, however your unit is orientated. Now, perimeter seals are the most common area of concern that we come across. They're typically a metal-to-metal seal, and in certain situations when you really have to minimize bypass, we can see a pillow seal. This augments a metal-to-metal seal. And the idea behind the pillow seal is it's flexible and it creates a gasket-type seal. As the unit reaches temperature, the thermal expansion compresses the pillow and it creates a tight seal that can provide a better performance. So pictured in this slide is a vertical angle that you can see coming up from the bottom left of your screen, extending upward. Directly behind that, directly downstream of that, is that big pillow material you see. And this picture was taken during a catalyst installation project that we were on. And the next module was going to be installed right where the person is standing, you can see in the picture. You can notice the pillow has a large depth to it, which creates a large surface area, which increases your ability to seal the reactor as that thermal expansion compresses that pillow over that surface area. All right, I want to move on to hardware. So another important consideration when you have new catalyst, or even if you just want to upgrade your system, is hardware. So catalyst comes in all different shapes and sizes, different operating conditions. So specifying the right hardware is a logical thing to do. This particular picture shows a unique clamping mechanism that was designed for a frameless system. Basically what happens is you have your small building block modules, and these clamps were designed to clamp all of those modules together and create what's essentially one large module. So having that arrangement allowed for large structural channels around the perimeter to support the catalyst, and you didn't need all of the individual frame members that are typically needed when you're needing to support individual modules. So this solution was especially appreciated by the end user. It reduced the cost of all that additional framework that you no longer need. All right, moving on to hoist and cranes. So one of the most potentially time-consuming aspects of your SCR changeout is the physical lifting of the modules in and out of your unit. For this reason, the development of a comprehensive lifting plan beforehand is essential for the changeout to run smoothly. So if you're looking at a crane option, cranes typically have significantly faster lifting and lowering speeds, which may be obvious, but this is extremely helpful when there's a large number of modules and you need a quick turnaround. If you're contemplating using a crane, a couple things to consider: size of the crane, staging area, clearance requirements, potential obstructions. There's also site traffic alterations that might be needed. So there's a number of factors to take into consideration if you're going to use a mobile crane for your changeout. The hoist and trolley systems have slower lifting and lowering speeds, but it doesn't mean that they have to be very far behind the mobile crane. The first thing that I recommend if you have a hoist and trolley system is optimizing your selection of the hoist and trolley. Even if you have one there, it might be wise, depending on your outage, to optimize that selection and change it out to a faster or more efficient system for your specific change out. Some things to consider is headroom, the weight of the modules, and there's a couple other factors, but that selection could be key. The second thing is, and it's often an overlooked thing, is potentially changing the arrangement of your hoist and trolley system. We've seen in the past that using such things as like a dual hoist and trolley system can minimize the amount of time you're watching that empty hook going up and down 60, 80, 100 feet at 10 feet per minute can get a little exhausting. So figuring out the best arrangement to maximize that time is key. And I think probably the most important thing after all that's said and done is having a crew that is well trained and coordinated to minimize the time that the lift is actually not taking place. That's a big key. Okay, so I wanted to talk a little bit about AIG performance. So whether you're looking to improve the system or you're replacing your catalyst, cleaning and tuning your ammonia delivery system is key. This process maximizes the performance and expected life of your catalyst. Now, one thing to keep in mind, it is important to clean your AIG prior to tuning. If you have a dirty AIG or if you have plugged nozzles, then manipulating your ammonia to try to get to some of the areas that are plugged could be a very frustrating process for your whoever's doing your tuning for you. So it's important to clean or make sure you have a clean AIG prior to tuning. So how do you know if your AIG is clean? First and most obvious is a visual inspection of the nozzles. So if your nozzles appear clean, you're on the right track. The second thing to mention is if your nozzles are clean, consider the orientation of your lances. Oftentimes the original or most common orientation is a horizontal lance with nozzles located at the top and the bottom of the lance. Now, rust and debris can accumulate in those lances. It's very common, and they can be blocking the holes from the inside of the lance. And it may look clear from the outside, but there may actually be debris blocking those nozzles on the inside. So just something to check for if you have that orientation. just look out for that. If you're online and you can't physically look at the AIG, you can use a stack testing company to manipulate a valve, and you're taking a reading from a specific point. And if you're manipulating that valve and you're not seeing any changes, that's another way it's an indication at least that your AIG might be plugged. So once you determine your AIG is clean or you're going to clean it, then you could think about AIG tuning. Tuning is typically performed by inserting a probe through ports in the ductwork. And basically what you do is you take samples in a grid pattern, and you can see how your ammonia and NOx are distributed. This is the traditionally accepted method. Now, regulations have been squeezing ever tighter and tighter, so it's become more important to take a large number of samples, and this allows you to more finely tune your AIG. In these cases, a permanent sampling grid is a recommended option. It's a useful tool. Permanent sampling grids are a system of permanent tubing that allow faster and more accurate sampling from an increased number of sampling points. So it's something to consider if that's something you need. All right, so now I want to take a deep dive into the importance of balancing your AIG system. So the plot on the left shows a correlation between ammonia slip and the NOx conversion requirement. There's a lot going on here, so I'm going to explain my way through this and follow along. So on the y-axis, ammonia slip is measured in ppm. And then along the x-axis, you got NOx conversion measured in percent. So that is percent of the NOx that needs to be converted to nitrogen and water, as Dave mentioned earlier. The various lines on the plot show the relationship between NOx conversion and ammonia slip, given a particular RMS distribution. So what is RMS? RMS is a root mean square deviation of all the points that were measured in the grid pattern we just spoke about. So in other simplified terms, it's a measure of the maldistribution of the ammonia to NOx ratio at the catalyst. So in other words, the higher percentage, the poorer the ammonia is distributed relative to the NOx profile. So as you can see, for any given NOx conversion requirement, the higher the RMS, the higher the ammonia slip. So to give some background and a little gauge on those values, my experience has been anything below 11% is definitely a tuned system, and the lower you go, the more finer and finer tuning the system is. So now you have all that in mind. The red line on this plot was drawn to call out all the systems that require 80% NOx conversion. So at this conversion requirement, the slip is between 1 and 3, no matter how well your AIG is tuned. And that's why this is a walk in the park. You could see on the right, not a care in the world, probably saying, I've never even thought about tuning my AIG. And that's totally fine. That's the system that an 80% NOx conversion requirement system is working with. So moving that line to the right. So now we've bumped that line all the way up to 90% NOx conversion. This is when things get a little bit tougher. An RMS below 11% keeps you under 5 ppm ammonia slip, but any higher, and you could see how dramatic that increases. So if this is your system, I would equate it to a challenging hike, maybe difficult, but with proper planning, it's not the end of the world. You just want to keep your system tuned properly. So now I'm going to bump that line even further to the right, all the way to 96%. And look at that, we went too far. The regulations got you. And now you got to literally climb Mount Everest just to meet emissions. And there's nothing you can do about it, right? It looks like it takes 3% RMS just to get under the 10 ppm ammonia slip. It's absolutely crazy. But what do you do if this is you? I guess is the big question, right? So my advice, don't lose hope. People make it to the top. You can too. It just takes a little more preparation. So this type of a system is considered like the Ferrari of SCR systems. It's high maintenance, but proper design, proper maintenance, and you'll be surprised what it could do. So the bottom line here with all these plots is I just wanted you to get across to take a look at your NOx conversion requirement, take a look at your ammonia slip limit, find out which of these systems you're working with, and it's going to help you make decisions on what kind of system upgrades or improvements or maintenance you should be looking at in your case. Do you improve the seals? Does a permanent sampling grid make sense? Is AIG tuning worthwhile? All those answers come a lot easier if you know where you fall on this graph. All right, I just want to jump to CO catalyst cleaning. Now, CO catalyst cleaning is not a very obvious thing when someone is talking about maximizing the performance of their SCR system. CO catalysts, also known as oxidation catalysts, they're designed to convert carbon monoxide to carbon dioxide. They're located just upstream of the AIG in some systems. The reason they're located in that particular place is if ammonia comes into contact with the CO catalyst, it will oxidize to create NOx. No one wants more NOx. So that's why we keep this upstream of the AIG. So with it being in that location and the CO catalyst, if that becomes plugged, you can create, bulk flow maldistribution to the AIG and SCR system, which can create a headache when you're trying to balance that system and maximize its performance. You create pockets of high flow, low flow, and it just makes everything more difficult downstream. So it's important to keep that clean. This is also true for units that don't have CO catalyst. Any equipment that's upstream, it's just another thing. Just keep in mind that the bulk flow to the AIG and SCR system, it does make a difference when you're trying to maximize performance.
Fantastic. Thanks, Rye. There's two more considerations on the contractor side that I wanted to introduce before we get into the case studies. And I'm not going to have any analogies that push people off mountains, but that was fantastic comparison. Thanks. One thing to consider, in addition to everything that Ryan and Dave have talked about, is module size. It is important to note because the module size might change in the OEM design for replacement for multiple reasons. When this is the case, we need to make sure that there's no loading hindrances. These loading hindrances can be anything from, additional housing infrastructure on the top of the unit, conduit for testing lines, or very obvious structural supports inside or outside the unit. In most cases, it's very possible to make modifications even in the structural hindrance situations. We can accommodate a larger module by making these structural modifications before and after to accommodate. So it's very important to plan in advance so we can ensure the project stays on schedule and we're prepared for this scope. Turnkey capability and accountability of a project, I think, are paramount. There's two paths to save money and be more efficient during any outage or turnaround. The first that I want to mention is indirect savings or soft cost savings. Having one vendor manage multiple facets of a project can effectively reduce vendor count. This reduces the number of touches and simplifies the complex contract management that every company has that function internally. So in turn, we're reducing the PO cost and soft cost savings of any project before, during, and after the project. Accountability is also key here because, the other way to put it is you have one throat to choke. Instead of having three vendors, you've got one vendor to hold accountable who's proficient and competent with that scope of work. The second is direct cost savings. This is the more obvious one that the asset managers and purchasing and accounting folks look at. But the black and white number, if there's one contractor managing multiple functions, this minimizes mobilization costs exponentially. Additionally, you're able to take advantage of a pass-through catalyst costing from the contractor themselves. You hire the contractor with the capability and program to support this. You can take advantage of buying that catalyst, getting the install complete with full transparency of costing through and through, and no markup. So a few different things to consider by working with one competent expert in the field. Now that we've had the chance to introduce different steps and considerations of a project, we want to talk on a few case studies. First off, on Groome's side, I'm going to discuss case study at a power gen facility that was looking for turnkey management for catalyst replacement. Now, turnkey might mean different things to many different people. In this particular situation, they wanted an outfit to handle 5 different functions. The first was new catalyst installation, old catalyst disposal, engineering of the project, scaffolding, and tuning. I think the tuning is the most understated of them all because we want to make sure that the catalyst is set up for success once that project is complete. Now the plant had 2 units and wanted to replace in one. I think that is a fantastic opportunity to use the second unit as a control to monitor performance gains over the next year, which we were able to do. The plant was very excited about the project and forthcoming with unit details, including drawings and run data, so we can come up with this case study. Now, unexpectedly, no matter how forthcoming they were and how detailed the drawings were, they weren't 100% accurate. So, this is a lesson learned that I think is very important to highlight and everyone needs to consider. The top door was noted that it was flange bolted onto on the drawing itself, but in actuality, it was also welded. This added labor and demand time, obviously. But fortunately, the Groom crew traveled very well prepared. We had the tools and talent to complete the work on schedule. So the extra torch and welding time weren't as much of a consideration, but we will consider that money saved or found money by avoiding any potential change orders. Now, additionally, the catalyst itself performed extremely well. The DP dropped nearly 2 inches at 1.8 inches. This impacted 3 main factors to save the plant money and show ROI in fuel savings, power output, and ammonia consumption. And here's the numbers with some graphs to illustrate them. So there's 4 layers of return on investment here. First off, with fuel savings at 1.8 DP improvement, the plant was able to realize $87,000 in fuel savings with less pressure on that turbine. $350,000 is a staggering number in ammonia consumption reduction. This is due to a 23% decrease from the new catalyst design. Third, in change order avoidance, that can be amounted between 15 and 20,000. And finally, one thing that sometimes plants consider and sometimes they don't is the opportunity for revenue gain. The plant was able to realize a megawatt increase and $39,000 in added revenue. All in all, it was just short of $500,000 in total ROI, which I think is a market improvement, and anyone who puts this project together would certainly get a pat on the back. I'm going to pass it off to Dave to discuss case study number 2.
Yep, so I wanted to apologize in advance. The fire alarm was going off in my office. So for everyone hearing this, I apologize. I came to the office second time in 4 months, try to get away from my little kids, and this happens. So
safety first, Dave. Do we need to take over for you?
I'm going down with the ship. So just real quick, I'll go briefly through this. This is an OTSG. For those who aren't familiar with it, it's a gas turbine that actually runs dry and wet. When it runs wet is typical Hershey temperatures. Dry goes up to 920 Fahrenheit. So we have to design these a little bit differently than we normally do. If you want to go next slide. So what happened is the plant, they were designed to run dry, which was 920 Fahrenheit, but the original catalyst load wasn't actually designed for that rating. So we worked with the plant and we came up with a new catalyst configuration where we took out their CO catalyst and replaced it with the dual function catalyst. If you want to go to the next slide. Yep, so we took out their CO catalyst, we sent it down to recycling, got the value out of it. That was used to offset some of the cost of the new catalyst. And then we went in with a design for the DeNOx catalyst that was rated for the high temperature, and then added some of the dual function catalyst right on top of that layer to take care of all the CO and VOC. If you want to go to the next slide. Yeah, so just here's a quick screenshot of their unit while it's running. So they were actually able to save about inch and a half of pressure drop on the unit while it was running. And they had greater CO and VOC conversion and much higher DeNOx than they had before. So all in all, this conversion to a dual function system was a win. So I'll put myself back on mute so you guys don't have to hear that buzzing in the background, and I'll jump.
Thanks, Dave. If nothing else, it sounds like what you've got to say is very important with the sirens in the back. So thank you. I love the last slide with the illustration, a screenshot direct from the plant. Can't say it any better. So very powerful slide. With that said, in the sake of time, I want to, highlight 5 key takeaways from what we were able to cover in the short 40 minutes we had with you all before we get to the questions. First off, whenever you have a permit, conversion, masking, back pressure issue of some sort, please consider all 10 factors of the SCR life cycle prior to making any decisions. It might not be the problem that you expect or that someone tells you without considering everything. Second, was your system designed for how it's currently running? Many times, likely not the case. As Dave mentioned, a lot of units are 5, 10, 20 plus years old. When replacing, avoid the knee-jerk reaction to replace in kind right away for obvious reasons. If you need consultation on that, there's many companies out there who are competent to do so. Please feel free to give us a call if you have any issues. Third, every system is unique. Consider consulting with the experts, particularly on upcoming retrofits. There's a lot of those coming up. There's a buzz in the air, a lot on the West Coast, as our refining and petrochem reps, Mark and Ray, have been finding. Please feel free to be open up front. Doesn't matter if that project is 4 months or 4 years out. It's best to get in at the ground level and start planning as soon as possible. With that said, just as things have changed over the past 20 years, things will change again. So this getting in at the ground level is important to allow for proactive design and maintenance measures. This way we could set it and forget it in design of your system so you don't paint yourself into a corner and make any rush judgments. Lastly, accountability is key. The importance of a turnkey service is paramount, and it will lead to superior cost savings and efficiency in your unit. So with that said, as you'll see, myself, Ryan, and Dave's contact information is up on the screen. Please feel free to ask questions or reach out to us on SCR or anything else that you might have questions with. It's great. The first question is actually a greeting from Spain. So I appreciate that. Thank you very much, Alfredo. The second question that we'll address here is, in the current COVID climate, is there any special planning that are required now during an outage? I think that's an extremely topical note. And one thing that we didn't mention, because it's not SCR specific, is COVID cleaning services. We do have a disinfection and cleaning division that's been very complimentary of our outage and turnaround work since March. It's enabled us to add an additional turnkey function to make sure that not only do we keep a turnaround or outage on schedule and prevent it from getting pushed, so to speak, but also keep it safe. No matter if you have Groome as the only contractor on site, or there's 30 other contractors planned to be on site. We want to address high touch areas, anything from bathrooms to office areas, and do a daily sweep for those hard non-porous areas or surfaces to disinfect them. So we have been using an EPA approved disinfectant, and it's been very effective. If you have additional questions on, COVID services, please feel free to reach out. As you saw on our second slide, I believe, we did do a webinar on that as well. So there's plenty of technologies and programs out there. We believe that we found the most effective. So another question, can you provide some pressure drop values for revamping design, 5 PSI?
I could jump on real quick. Sorry for the noise again. So we'd have to look at the individual reactor size, the application. So it's not something I could just say, this is going to be it. We have to look at the actual case and see what catalyst is in there now, or what pitch we can put in there. So to be honest, I couldn't answer much for this question right now.
Alfredo, it's a good question, but we're going to need some more specifics on that. Please feel free to reach out to any one of us or all of us, and we can dig in a little bit more on that for you. But thank you. Got a question on the power gen side with a Hersig unit, Neuter Erickson, with 7 FAs. With burning natural gas, what is a typical lifespan of an SCR catalyst? The current OEM is Cormatec. Dave, do you want to touch on lifespan?
Yeah, another thing. Sorry, I'm going to say it all depends a lot, but it depends on what catalyst is in there, the depth of the catalyst. Typically natural gas units, they just deactivate slowly. It's more of a thermal deactivation, whether it's our catalyst or Cormatec's catalyst. We could look at the design of what's in there and kind of give an idea, but if you do know your ammonia slip and your current DNOx, that should give you at least some indication of what your lifespan is left from the original design, what was quoted to you.
Great, thanks, Dave. We've got a few more questions. I want to kind of get through these for everybody. So we've got a question here on SCR grids. Do you service only SCR grids? We have a waste boiler with 2 VOC grids and an SCR grid. It operates at temps in excess of 1200 F. Dave, we'd certainly like to see the design of your unit and what needs to be performed there. What are the contaminants? How long is your outage? What's the access? Well, we could certainly look at helping you out with that project.
Yep. From our side on a Hersig, we want to see permanent test grids on every new Hersig there is. I think it's going to save you a lot of trouble down the road. On smaller units, it might be easier to stick a probe in there and find out what you need. Is that?
Yeah, another thing, Dave, that I'd like to discuss is, your use of grid. Are you referring to a permanent sampling grid or the module frame assembly itself? There's a few things that we'd like to, review with you there specifically. It looks like some folks posted questions on the chat board as well. There's some questions that look like they popped up a little bit into our presentation. So Josh, please feel free to reach out to us specifically on what your question was there. Here's a good question. Do particulates that sit on the catalyst significantly contribute to metals poisoning other than just blocking access physically? Or do the metals need to be vaporized and transported in an active form? Right, you have a perspective on that?
Yeah,
Sure.
Go ahead, Ryan.
No, I think it all depends on the specific contaminant that we're discussing here. Unfortunately, I hate to give that answer again. Depending on your specific situation, what's contaminating it, how it's depositing, you can, have poisoning. Poisoning is definitely something that can happen in the catalyst, and it doesn't have to be in a specific form to happen that way. So I just need a little more specifics on that.
These are all great questions, everybody. I know that everyone wants to give the exact specifics on their units, which is totally understood and appreciated, please feel free to use our contact information. We can dig in one-on-one with you once this call is complete. Okay, so David got back to us on the grid. He's referring to the module frame assembly and not the permanent sampling grid itself. So yeah, we'd still want to look at what the contaminant is, unit access, et cetera. So David, please feel free to reach out to us. I think it's been a fantastic, opportunity to work with David Umicore and the team over there. Thank you everyone for taking the time to hop on. It seems like there's a lot of interest and questions from different respective areas of the SCR replacement and service field. So in the sake of everyone's time, please feel free to reach out to us one-on-one. We'll be following up with you as well. And we appreciate it. Have a great and safe rest of your day. Take care.